All right, welcome back, my friends. This is William M. Briggs on episode 51 of Uncertainty and Probability Theory, the Logic of Science. We're just about to start parameters. Parameters and models. We did the introduction about models, what models are. We're going to be, models are anything. This is a model right here. Whenever we have a probability, whenever we have a relation between propositions, here's a collection of propositions. And here's another proposition we want to judge in relation to these two. That's what a model is. That's all a model is. That's all probability is. That's all logic is. Relation between propositions. The relation between these propositions is our study. We don't necessarily have access to where these propositions arise, where they come from, and so forth. And so this has kind of fueled a false vision of probability. And I want to handle this. We've talked about Bayesian theory. Of course, we've proved Bayesian theory is the very form of probability. If probability is a number, when it's a number, it's recognized or represented mathematically by Bayes' formula. So there's absolutely nothing wrong with Bayes' formula. But as a philosophy, we need to be very careful about what the Bayesian sort of philosophy is. And we're going to talk in depth about this when we start to talk about formal models. This is a schematic or a schema for all models of every kind. But of course, in science, we have these very formalized, parameterized models and so forth. So we're going to talk about them. But remember, these are always a subset. These formal parameterized models that we're talking about are not the models. They're a subset of all models of all uncertainty. All uncertainty and all logic is just, you have this proposition, which can be very long and complicated. Then you have this proposition, which can be very long and complicated or short and sweet. And you want the relation between them. That's it. That's all it is, just the relation. That's why I like this bar right here. This is the relation bar. That emphasizes that we're talking about two things. And that brings up another point, which we've talked about many, many times. But it is impossible that this exists. And we talked about this shorthand notation. There is no such thing as a probability of a proposition. No proposition has a probability. Probability is since it's a relation, there has to be something it is related to. A lot of times we don't write down everything that we know about these propositions. Remember, this contains absolutely everything we know about the propositions. The definition of all the words, the symbols used, all that kind of thing. All these tacit and implicit pieces of evidence or premises that go into these propositions. They're all there. They're always there. And so when you see people writing things like this, perhaps it's just a shorthand for them to do easy calculations on paper. They're carrying through things like that. Nothing wrong with that. But when they write things like this, something has gone wrong. An absolute error has taken place because they have suppressed all this stuff after the relationship bar. And they assume you just agree with them about what it is. You may or you may not. And if you don't put that stuff there, it's going to get lost. And then all of a sudden, this thing takes on a life of its own, this probability of y itself. So for those who disagree, I invite you as homework, try to think of a proposition that you want to assign a probability to. A physical thing, a mental thing, anything that, whatever, a measure in the world, whatever you like. And you try to see if you can write down that probability without any conditions. I invite you to try this, especially those who believe probability is real or physical, that it exists in the world much as like height does, or reactance does, or capacitance does, or something like this. You go ahead and try to do that, and I think you'll find that that homework exercise extremely instructive. It doesn't exist. And the reason to emphasize all this is because, again, we don't necessarily supply these premises. These are given to us by the problems that we want to solve. We decide the propositions of interest, which I always call the stuff on the left-hand side right here, and that's a subjective matter. These are the things that are important to me, so they're subjective in that sense. These bits over here are the bits of evidence that we say are important in respect or probative of this proposition of interest. These too are to a great deal subjective. And so people have the idea that probability is subjective, but it isn't. It absolutely is not. Once you set these, we did this just a couple of weeks ago. If we have x plus 7 equals 11, and we want the probability that x equals 5, a subjective probabilist can say the probability that x equals 5 is whatever he likes, any number between 0 and 1. Probability, however, is entirely objective. Once we set these propositions, once we set this proposition, however they arise, the relation then is just a strict matter of logic. It doesn't mean a number can always be assigned. We can't always assign numbers to probabilities. But when we can assign numbers, or even if we can't, the relation between the propositions is entirely logical, purely objective. So you'll see people out there, they'll say, they'll present Bayes' formula, which is what this is right here. Let me get rid of this business. They'll present Bayes' formula to you, and they'll say, it's just Bayes' formula, everything else is in the details or whatever. And we're just updating our beliefs and all that kind of stuff. So that's what I want to talk about today. That stuff is wrong. There's well-known people out there who tout this kind of stuff, and it's just false. It's not right. It's absolutely not right. So let's go through this. We have the idea that Bayes' theorem updates probabilities. So you'll hear that a lot. And that's not wrong. It's not wrong, but it's not necessarily right either. It's not necessarily always helpful. So I'm going to lead you through an extremely simple example to show you that Bayes' theorem itself, of which there's nothing wrong with the math. There's never anything wrong with the math in Bayes' theorem. Absolutely never. We proved Bayes' theorem. That was one of the first things we did. We proved it from first principles. From absolute basic premises about how we wanted our measures of uncertainty to go. So we know Bayes' theorem is correct, but it doesn't mean we have to use it. It's a very helpful formula, very useful formula, but it doesn't mean it's always useful or always helpful or should always be invoked. And it is certainly not a philosophy in and of itself. We have the philosophy of probability. That's what we're interested in. That's what we have to stick to. Okay. So with all that malarkey out of the way, let me turn this heat off. It's darn cold up here. We set record low temperatures, you know, the last 100 years, however many the thermometers have been in place. So global warming is causing quite a lot of cold air recently. It's been a long, brutal winter. So I have this heater running out here in the shack, and it gets hot sometimes. Okay, we have a device, a machine, a thing, real or not, it doesn't make any difference. And my evidence is it can be in one of three states, and only one. It can be in state 1, or state 2, or state 3. It must be in one of those. That's the evidence I'm going to assume, subjectively chosen. And I want to know, given this evidence alone, what is the probability that it is in state 1? Well, we've did this many times. We've proved because of the laws of probability and so forth that this is 1/3. Easy to see, right? It could be in S1 or S2 or state 1, 2, or 3. What's the probability it's in state 1? Given only this information and none other. This information, this is another trick people pull. We write this stuff, if they don't write this stuff out explicitly, they'll put in all sorts of other stuff that they just insert it. Oh, it's common sense, it's there. It's not common sense, it's there. You have to be explicit about what your propositions are. We're going to see that when we do modeling, the formal aspects of modeling ad nauseum, so I won't emphasize that today. All right, so suppose later we learn, in addition to x, we learned W. This machine has malfunctioned, we're told, and it can't be in S3. All right, so now we want the probability of y given x and w. That's very easy to see. Well, if it can't be in state 3, it can only be in state 1 or state 2. So the probability it's in state 1 is a half. Boom. Probability is taking all the evidence we consider probative and given about our proposition of interest, and we state the probability of it. That's it. We don't need Bayes' theorem to do this, and in fact, I'm going to lead you through the example here. It works. The math works. I promise you the math works. But it's confusing, and it's arduous, and it takes us down a path that we don't need to go. There's nothing wrong with going down that path if you like the labor of going down the path, but it's not necessary. Okay, so this is very easy to see. We've taken all the evidence that we have, and we have the probability now of a half. And this right here in itself is proof that this proposition, at least, and all propositions, doesn't have a probability. The probability changes with respect to the evidence. You change the evidence, you change the probability. That right there is going to be an enormously controversial statement when we come to these formal models. People forget that if you change the evidence, of course you change the probability. That's not a bug. That's a feature. That's the way probability is. Because they all tend to think, once we start talking about real measurable propositions in the world, they come to think that these things have probabilities. And we've talked about this so many times. Nothing is imbued with, nothing consists of a probability. It's not a real force. It's not a real attribute. It does not exist in the world. It's only in our minds. And our minds are, and these rational thoughts are immaterial. But that's an entirely different thing. So let's just go through this Bayes' theorem here. We'll work out the math and see that it must be exactly the same, but it's going to be a little bit more tedious. Well, here is our prior distribution. Here is our prior. Given just x, we want the probability y is S1. Well, probability that's in state 1, given it's S1, 2, or 3, is a third. Okay. Let's write this up here. And here's that same probability down in the denominator, so I'll write it down here too. And we need to fill in, this is going to be plus, and that's going to be something here. So now we want the probability that it's not in state 3, given that it is in state 1. We now assume that this is just Bayes' theorem. We're just applying Bayes' theorem. We can manipulate these symbols. X says it can be in S1, 2, or 3. Fine. Now, Y is insisting it is in state 1. So the probability it is not in state 3, given that it is definitely in 1, the probability is not 3. Well, that probability is 1. It is certain. We have deduced that this is true because we have said it's in state 1. The probability it is not state 3 is, of course, 1. And that's the same, down here in the denominator. Now here, this is the total probability formula, which is part of Bayes' formula. I use the y complement to mean, in Boolean terms, not y, or y is false. There's lots of different ways to write that. You know, you can write y, you can write y complement. There's all kind of different ways in logic that you could write that. There's no consistent way that I'm aware of. Everybody takes a preference to this, but I don't. Sometimes I'll just write not y. I think since we're dealing with propositions and Boolean calculus and so forth, sometimes it's just easier to do that. Okay, it doesn't matter. So over here, the probability that x can be, again, S1, 2, or 3, and the probability it is not in S1, because that's what y complements, the probability is not S1, well, it has to be 2/3, because if it's not in S1, it can only be in S2 or S3, and the probability, therefore, is 2/3. Now we need the probability that, given, this is where it gets kind of confusing, given that this is true, it's not S1, and given it could be X1 or X2 or X3, what's the probability that it's going to be not S3? Well, that's a half. Works out fine. Let me erase some of this here. Works out fine, and then we could just, we could cancel all the 3's, and then we have a 1. And then we cancel all the 3's, the 2's cancel, and so we have 1 over 1 plus 1, which equals 1/2, which works, no problem. But sometimes this kind of thing can get confusing when you're starting to think about this. The probability it's not S1, okay. It's not an S1, so it's got to be an S2 or S3. And the probability it's going to be not S3 is therefore going to be, well, wait, this is not causal. We're not saying it's causal, so therefore we have the possibility it could still be S3. It could still be S3. We're not deducing that it's not S3. We're saying, what's the probability it's not S3? And so we could have S2 or S3, so that must be a half. But notice the contortions we have to get. We got there, it's fine, we've deduced it, but it becomes a bit of a puzzle. Whereas before, when we just look at this stuff, we just take our total evidence, whatever our total evidence is, and we want the probability. Sometimes Bayes' formula, like I say, it aids us in calculating this. And sometimes, while it always works, it causes us a lot of extra work. And so it's not necessarily true that Bayes is updating our beliefs. We just take all the evidence that we have and we calculate the proposition of interest, the relation between the evidence we believe and the proposition of interest, and that's it. That's all Bayes' theorem, that's all probability is. And I've said it 10 times already, but this is fine. It's no problem, and sometimes it's very, exceedingly useful, as we'll see, but it's not necessary. It's not always necessary. And so we kind of, because we want to keep the math, we want to keep Bayes' theorem and all this kind of a thing, we always we develop this weird language of priors and posteriors, and it just teaches us, we come to believe that this thing does have a probability somehow or another. It just leads us down this path, as we'll see. As we see next time, I'm going to start talking about how the origin of these parameters and so forth, the parameterized models and whatnot. And I've warned us at the very beginning, you are going to believe, even though I've said it, I don't know how many times, somebody can go back and count today, that nothing has a probability. You'll begin to believe that things do have a probability. Because this math, this is a very simple example, but the math becomes very elegant and difficult. And once you work it all through, you feel a sense of accomplishment, real. And that math becomes alive. The math will begin to become alive for you. I've warned you about this. I'm telling you again. I'm going to tell you when we do it. And then after we do it, you're still going to see that the math has somehow come alive for you. The math will become realer than reality. This is the modeler's dilemma. It's almost impossible to avoid. But avoid it you must. And we must always keep this kind of stuff in mind. So that's all Bayes' theorem is. Bayes' theorem is just a useful formula. There's no philosophy to it. The philosophy is the philosophy of probability. And that philosophy is just logic. We have some set of premises, evidence, whatever we're going to accept over here, whether it's true or not, doesn't matter. We're accepting it as true. And we have some other proposition we want to relate it to. And we're interested in the relationship. What's the relation between those two sets? That's it. It's just a relation between sets and nothing more. All right, that's it. Next time we start on the more hardcore math. It's going to get a little bit more difficult and so forth, but we really need to tackle these parameters. All right, very short class this time. Well, not entirely short, but shorter. Thanks very much for listening.